Bismillahirrahmanirrahim. Assalamualaikum dear students. I hope you all are fine and in the best conditions of your health. So in today's lecture for the course of organic synthesis, we will discuss about the type of organic phase transfer catalysis processes. So far we have discussed about what is phase transfer catalyst, what are different types of phase transfer catalyst. Now we will discuss about what are different types of phase transfer catalysis processes. So the key concepts of this lecture we will discuss briefly again about the phase transfer catalysis. So we'll have a review on what is PTC. We will also have a brief review on what's the mechanism of phase transfer catalyst, and then we shall discuss about the type of phase transfer catalysis processes. Right? So you know that whenever there is a problem when there is a solution in which there are reagents in different phases, then the problem of solubility arises, right? For example, consider a simple substitution reaction. So suppose that we have an alkyl halide Rx and we have a nucleophile Y negative, right? So this nucleophile is soluble in water, while the organic solvent is while the organic alkyl halide is soluble in the organic solvent. The reaction always goes on, reaction always works when both of the reagents are in the same solvent, when they are in the same phases. But in case if two reagents are in different phases, the reaction cannot occur. So it's very important for us to bring one of the reagent in the other phase, so that both the reagents become in single phase and the reaction works. Right? But we cannot bring an aqua-soluble inorganic reagent into the organic phase. Right? So what can we do in this situation? We make use of a reagent that will bring the inorganic reagent from aqueous phase to the organic phase, right? So for example, consider that we have a situation in which the inorganic anion is in aqueous phase while the organic reagent is in organic phase. Just consider that organic phase is the light blue color, the lower layer, while the aqueous phase is on the top. Here you can see that both phases are separated, they are not combined together. So the reaction will not work until we add something that will bring the inorganic reagent into the organic phase. Right? In this case, one possibility in order to solve this problem is that we can make use of some organic solvent which are just like water. Right? So in case if we are having a problem that the inorganic reagent is not getting dissolved in the organic solvent, so one possibility is that we can make use of organic solvent which is just like water, such as alcohols. Right, so the alcohol will have a hydrophilic part, the hydroxyl group, and it also has an alkyl group which is hydrophilic. Right, so it will have the association with the organic phase because of its lipophilic alkyl part, and it will have association with the inorganic reagent because of the hydroxyl group here. But here what happens, the problem is that alcohols or other water-like solvents, they solvate the nucleophile. They surround the nucleophile, so the nucleophile is not free to react. So we say that nucleophile has become trapped in the solvent cage. It's not available. So the reaction becomes slow. Solvation decreases the rate of reaction, which is not desired, right? So we need a free nucleophile. We need a free naked anion that's available for reaction. Right? So that's why we're not making use of water-like solvents, because in that situation, the water-like solvents, they will solvate the anion and will decrease the rate of reaction. So here the problem can only be solved if we make use of phase transfer catalyst. So what is a phase transfer catalyst? Is a special type of heterogeneous catalyst, and it facilitates the migration of the reagent or reactant from one phase to another. So it's normally the inorganic reagent which is being transferred from the aqueous phase to the organic phase. Right? So just always remember, it's always the inorganic reagent which is being transferred from the aqueous phase to the organic phase, right? So nothing is being shifted from the organic phase to the aqueous phase. If you do not make use of this phase transfer catalyst, then in such case the reaction is usually slow or inefficient, and in the certain circumstances these reactions do not work at all. Right? So it's very important for the two species, for the two reactants to be in the same phase, and this work of bringing the two phases together in a single solvent or in the single phase, that's done by the phase transfer catalyst. Right? The substrates and anion are brought together by this phase transfer catalyst, which transports the anion into the aqueous phase, into the organic phase, so that it can react with your substrate. Right? So just example, that we have an alkyl halide which is soluble in the aqueous phase, in the organic phase, and we have an anion, so cyanide ion, which prefers to be the aqueous phase, right? So in case you want to carry out the substitution reaction of the alkyl halide with cyanide, then in that case it's very important that you make use of phase transfer catalyst. Because if you do not make use of phase transfer catalyst, then cyanide will not be able to react with alkyl halide, right? So once you add the phase transfer catalyst will carry the cyanide into the organic phase so that it can react with your substrate, right? So by means of phase transfer catalyst, we are not only transferring the inorganic species from the aqueous phase to organic phase, but we are also activating it, and we are increasing the rate of reaction, right? So once the inorganic anion or your nucleophile is being shifted from aqueous phase to the organic phase, you know that in aqueous phase the anion is solvated by water, but once this anion is inside the organic phase, so the organic solvent is not solvating the anion, right? So because the anion is now free, it can easily react with your substrate, so the rate of reaction increases under phase transfer catalysis conditions. So briefly we'll consider about the advantages of the phase transfer catalyst. You know that when you are using the phase transfer catalyst, you do not need to worry about the anhydrous conditions or use of aprotic solvent, because the phase transfer catalyst is already using water, so you do not need to make the conditions anhydrous, right? Also, the phase transfer catalysts occur at lower reaction temperatures. You do not need refluxing conditions. They are easy to work up in most of the cases. So instead of making use of very expensive bases like sodium hydride, sodium metal, which are very sensitive to water, you can just simply make use of cheaper alkali metal hydroxide. So these is no problem of sensitivity or reactivity with water. Also, they are cheap enough, so you can make use of them in any amount that you require. Also, as already mentioned, there is no need to maintain the anhydrous condition, as well as since we are already making use of water. They are highly selective reactions. They have high yields, and some reactions that don't work under normal conditions, they can easily be carried out under phase transfer catalyst conditions. Right? So there are a number of reactions which do not work at all, and they work very efficiently under phase transfer conditions. The reason being that is that under such conditions the inorganic reagent is soluble in water, and since it's not being transferred to the organic phase, that's why the reaction is not working at all. But just adding the phase transfer catalyst, the reaction works well. So these are the different phase transfer catalysts. So we have quaternary ammonium salts, right? So in quaternary ammonium salts we have central nitrogen, which is positively charged, and we have the negatively charged counter ion that's neutralizing the positive charge on the nitrogen. So it's very important that your phase transfer catalyst should be overall neutral, right? So therefore, whenever there is a positive charge, there should always be a negative charge which is countering that positive charge right here. So it's very important also that the phase transfer catalyst must have a larger organic part. So the organic section should be larger. So in general, it has been observed that number of carbons in any phase transfer catalyst should be at least 15. It should not be lower than 15, because if number of carbon is less than 15, in that case the phase transfer catalyst will not work efficiently. Okay? Then we have cinchona-alkali derived quaternary ammonium salts. Right? The work is seen that we should have larger organic part, and the organic part should be non-polar. Right? The organic part should be non-polar, because if you have some polar functional group on the organic part, in that case the solubility of the phase transfer catalyst in the organic solvent will decrease. So we want to have a larger organic part so that the phase transfer catalyst has more solubility in the organic phase. Next we have fedrine derived catalyst. Again, we have nitrogen with positive charge here, so in order to neutralize that positive charge we have some negatively charged species, which is normally a halogen. So in case if you have a chiral center in your phase transfer catalyst, as you're seeing here, then in such cases these phase transfer catalysts can be used as chiral catalyst as well. Right, so you can carry out the asymmetric synthesis or enantioselective synthesis when you are using the phase transfer catalyst as chiral catalyst. Next we have quaternary phosphonium salts, in which the central atom is phosphorus, right? Again, the negative part of normally the halogen, it is neutralizing the positive charge. Again, you can see that here the organic part is larger and the organic part should be larger and unpolar. Then we have crown ethers and polyethylene glycol, also known as PEG. So here again we have the carbon chain, which is forming the most part of the skeleton. And in crown ethers we are having cyclic systems. The crown ethers have the ability to trap the positive charge, positively part of the inorganic reagent. So this oxygen of the crown ether will trap the positive part of the metal, the positively charged metal inside the cyclic system. So in order to maintain the electronic neutrality, so the negative part of the inorganic reagent will follow this complex crown ether into the organic phase. In that way, your anion will just get into the organic phase from the aqueous phase. Right. So different type of reactions that are catalyzed by phase transfer catalyst include the SN2 displacement reactions. So here you can displace different groups by halide, cyanide, azide, carboxylate, hydroxide, alkoxide, phenoxide, thiophenoxide, etc. Right? So you can carry out almost all type of SN2 displacement reactions. And we can carry out alkylation reaction, whether there's alkylation of carbon, that's called C alkylation. If you carry out alkylation on nitrogen, this is called N alkylation. If you are getting out alkylation in sulfur, this is called S alkylation. And if you are getting out alkylation on oxygen, this is called O alkylation. So you can carry out all type of alkylation reactions by means of phase transfer catalyzed reactions. Also we can carry out elimination reaction, oxidation reaction, reduction reactions, polymerization reaction, deuterium exchange reactions. So almost all type of reactions can be carried out by these phase transfer catalyst conditions. So basic requirement for a phase transfer catalyst is that the phase transfer catalyst must have the ability to transfer the inorganic reagent from aqueous phase to the organic phase. Secondly, the reagent should be highly active in organic phase. So the solvent you are using in the organic phase should not have the ability to solvate your anion. It's very important. The organic solvent should not solvate your inorganic reagent, because if the organic phase is also solvating the so your phase transfer catalyst must have the ability to transfer the inorganic reagent from aqueous phase to organic phase. Further, the reagent which has been transferred should be active in the organic phase, because the organic solvent is not solvating the anion. Right? But if the organic solvent is solvating the anion, the rate of reaction should decrease. So you have to make use of a solvent which is suitable, and you should not be able to solvate your anion. Right? Next, that the catalyst you're using should be cationic. It should have positive charge, and the cationic should be organic in nature. So you should be having a larger organic structure, so that the organic structure can have more association with the organic phase. Then the cation and anionic bonding in the phase transfer catalyst must be loose, right? The cation and anion must not be very strongly bonded to each other, because we want the anion to be exchanged with the other anion of the inorganic species, right? So the attraction between the cation and anion should always be loose. Further, the phase transfer catalyst must be stable under reaction conditions. It should not take part in the reaction. It can be easily prepared and easily recovered, should be commercially cheap, and should promote selectivity. So these are the basic requirements for a phase transfer catalyst. But the basic criterion for the phase transfer catalyst is two. That is, number one, the phase transfer catalyst must have the ability to transfer the inorganic reagent from aqueous phase to organic phase, and secondly, the transferred inorganic reagent must be more active in the organic phase. That is, the organic solvent must not be able to solvate your anion. Now, there are different factors which affect the phase transfer catalyst conditions. Number one, the type of amount of catalyst. Right, so I told you earlier that the catalyst you are using should not have polar groups on it. And amount of catalyst, that the amount of catalyst, if you have larger amount of catalyst, then the reaction goes well, reaction gets speed up. So normally we make use of 10 to 15% of a phase transfer catalyst. Right. Then we have agitation. So it has been found that if the stirring speed or the agitation speed is faster, then in that case the rate of reaction increases, because whenever you are agitating the reaction, whenever you are stirring the reaction, what happens that the interfacial region between the organic phase and the inorganic phase increases. So what happens that whenever you are stirring, then small droplets, they arise from aqueous phase and they enter into the organic phase. So these droplets carry actually the phase transfer catalyst, which is bonded to your inorganic reagent into the organic phase. So faster the agitation, faster the stirring speed, greater will be the rate of reaction. Amount of water in aqueous phase is also very important, whether you are carrying out whatever type of phase transfer catalyst, but amount of water in aqueous phase is very important. It has been found that even if you are carrying out a phase transfer catalyst in the absence of water, still you have to add a little amount of water, right? So the presence of water is very, very important in phase transfer catalyst conditions. So the temperature depends on the reaction conditions. Certain phase transfer catalysts work at low temperature, and under certain conditions you have to increase the temperature as well in order to carry out or promote the transfer of phase transfer catalyst to the organic phase. Then we have organic solvents. So the organic solvent should be such that they do not solvate the inorganic anion. Right? This is the basic criterion for organic solvent. The organic solvent should be such that your organic substrate is solvent in it, and the organic solvent is not able to solvate your anionic species, because if it's able to solvate your anionic species, then in that case the rate of reaction will get lower. So these are the basic factors that affect the rate of phase transfer catalyst conditions. So type of the catalyst, amount of the catalyst, then we have agitation, then we have amount of solvent, amount of water, then we have temperature, and the organic solvent. The most important thing is organic solvent, that the organic solvent should be such that it does not solvate your anion. Now we will move to our basic topic, that's type of phase transfer catalysis processes, right? So we have studied about type of phase transfer catalyst, we studied about the potents, we studied about crown ethers, we studied about liquid ammonium salt spectra, but here we are talking about the phase transfer catalyst process, not type of phase transfer catalyst. So you know that phase transfer catalysis systems are characterized by presence of two phases, right? So we have organic phase and we have aqueous phase, and there is a layer between the organic and aqueous phase. So this layer, or the separation between the aqueous phase and organic phase, is called the interfacial region, right? So the layer or the region that is separating the two layers is called the interfacial region. So there must be at least one interfacial region. So phase transfer catalyst system has three parts, two phases and at least one interfacial region, right? So the reaction takes place in the interfacial region. It means the reaction always occurs between the aqueous and organic phase, or in case if you are not using the aqueous phase, then the reaction occurs between the solid phase and the organic phase. So in phase transfer catalyst we have actually two types of processes. The first process is that when reaction is occurring between organic phase and aqueous phase, since both layers are liquid, so that's why such phase transfer catalysts are called liquid phase transfer catalyst, or PTC, right? While the other type of system or other type of process is that when you are carrying out reaction between a solid phase, so it means that your inorganic reagent is in solid phase and we have organic reagent in the organic phase, right? So here we have a solid phase and a liquid phase. So such type of phase transfer catalyst processes are called solid liquid phase transfer catalyst, right? So this is called SLPTC, right? So we have LLPTC and SLPTC. So LLPTC is a situation, more common system in which your aqueous phase and organic phase are two phases, since they both are liquid, so that's why we are saying this phase transfer catalyst processes as LLPC, because both phases are liquids. But in case if one phase is solid and other is liquid, then in such case we call the process as solid liquid phase transfer process, right? So there are two processes of PTC, LLPTC and SLPTC. Firstly, we consider about LLPTC, or the liquid phase transfer catalyst. So it's the most common type of the two-phase methodology, right? So what happens that you dissolve the organic substrate into organic solvent and inorganic substrate into the aqueous layer or water. So since we have two layers with our liquids, so that's why we call it LLPTC. Another alternative is that instead of making use of aqueous solvent, you can make a concentrated solution of alkali or such as sodium hydroxide or potassium hydroxide, and the other phase is your organic phase, right? So the organic solvent should be non-polar and should be non-solvating. This is the major criterion. So in LLPTC we have two possibilities. Number one is that either you are dissolving the inorganic reagent into the aqueous phase, or second possibility is that you are making a very concentrated solution of alkali such as sodium hydroxide and potassium hydroxide in water, right? So this concentrated solution will act as the other liquid phase, right? So these reactions, the liquid-liquid PTC, they are not sensitive to water, right? So if you are having a reaction that's sensitive to water, you cannot carry out in liquid-liquid phase transfer catalyst, right? So the liquid-liquid catalyst system are only applicable in case if your reaction are not water sensitive, right? So there are basically two types of LLPTC. Number one, reactions that occur under neutral conditions, and number two, the reactions that occur in the presence of concentrated alkali solutions, right? So reactions that occur under neutral conditions in such system, what happens that we have organic substrate that is dissolved in non-polar organic solvent, and the inorganic reagent is in aqueous solvent, right? So we have dilute solution of our inorganic reagent in water, and we have a solution of our organic substrate in organic solvent. So the organic solvent should be non-polar, right? So this is example of neutral conditions system, and normally such reactions are used when you are carrying out aliphatic nucleophilic substitution reactions, right? So this reaction of LLPTC under neutral conditions, this is very suitable for reactions that involve aliphatic nucleophilic substitution reactions, right? For example, consider that we have 1-chlorooctanol and we want to substitute this chlorine with a cyanide. So we are making use of 1-chlorooctanol octane. So this 1-chlorooctane is soluble in organic solvent, while we have aqueous solution of sodium cyanide. So this aqueous solution of sodium cyanide is in water. So it happens that since both layers are separated, we want to shift the cyanide into aqueous phase, so we make use of phase transfer catalyst. So the phase transfer catalyst we normally use in this situation is tetrabutyl ammonium fluoride, and it's commonly called TBAF, right? So this TBAF is basically a phase transfer catalyst, and it will carry the inorganic reagent from aqueous phase to organic phase. So this reaction is almost complete, giving high yield in just 1 to 2 hours. Right, so you can see that how much the phase transfer catalyst is speeding up the reaction, right? So we get the cyano, octane, and very high yield in just 1 to 2 hours. This reaction does not occur at all in absence of phase transfer catalyst, right? So the use of neutral conditions under liquid-liquid phase transfer catalyst, these are very suitable for conditions for reactions that involve aliphatic nucleophilic substitution reactions. The other type of liquid-liquid phase transfer catalyst involves presence of concentrated aqueous alkali, right? So we have organic substrate dissolved in organic solvent, and we have the inorganic reagent used in the form of concentrated solution, right? So we are having sodium hydroxide or potassium hydroxide with very little amount of water, right? So this is an example of the concentrated aqueous alkali solution, right? So this is also very widely used in organic synthesis, and in this system what happens that your alkali, which is in the form of concentrated solution, it deprotonates the substrate, right? It will pick up a proton from your organic substrate, and as a result the organic substrate will be converted into anion, right? And further what happens that the other inorganic reagent will attack, right, and it will carry out the reaction. So such type of reactions are normally involve C-alkylation, N-alkylation, S-alkylation, generation of carbene via alpha elimination, autooxidation, nucleophilic addition reactions. All of these reactions, they can be carried out by making use of concentrated alkali solutions, right? So we are making use of concentrated aqueous alkali solutions. Again, since the two layers are liquid, one is your organic phase having organic substrate, and other is the concentrated aqueous alkali, which is also in the liquid form. So this is LLPTC, but since we are making use of concentrated alkali, so that's why it is example of the concentrated aqueous alkali LLPTC, right? So this is more application than the neutral conditions LLPTC, because the neutral conditions only suitable for systems which are water sensitive, which are not water sensitive, right? So in case you are using neutral conditions under LLPTC, you can only carry out the aliphatic nucleophilic substitution reaction, but when you are using concentrated aqueous alkali solution in LLPTC conditions, you can carry out reactions such as C alkylation, N alkylation, S alkylation, carbene generation, auto-oxidation, nucleophilic addition, etc. So this is having higher applications. Next we have solid liquid phase catalysis. So certain reactions don't work well in LLPTC conditions. If your reaction is sensitive to water, or if your reaction is sensitive to alkali, then in such cases what happens that we cannot carry out reaction under LLPTC conditions. So in this situation, what we do is that we make use of the inorganic reagent in solid space. So we are making use of solid inorganic reagent and organic system which is dissolved in aqueous phase. So here we have two types of systems. One is solid inorganic reagent and other is the organic solvent having the organic reagent in the liquid phase. So this is example of solid liquid system, right? So in this case, the solid ionic reagent is solubilized in organic medium with the help of ground ethers, right? So whenever you are using the SLPTC, solid liquid phase transfer catalyst, then normally the phase transfer catalyst we use is the ground ether. The ground ether, what happens that it will just trap the positive charge of the inorganic anion, inorganic species, and the negative charge will follow the ground ether into the organic phase. So example of such reactions is the substitution of benzyl halide with potassium cyanide. So here we are using potassium cyanide in solid phase, right? We are using potassium cyanide in solid form, and we are using benzyl halide in toluene. So toluene is a nonpolar solvent, it will not solvate your anion. What happens that we make use of ground ether. So in this specific case, the ground ether that was used is 18 crown 6 ether, right? So this ground ether will trap the potassium inside the oxygen ring, right? And the cyanide will follow this complex ground ether into the toluene, right? So in that way the cyanide, since it's not solvated by the anion, so it's not solvated by the toluene, so the cyanide will attack on your benzyl chloride and resulting in formation of benzyl cyanide or benzyl nitrile in the here, right? So this is an example of solid liquid phase catalysis, right? It has been proposed that the presence of little water is compulsory for such reactions, although the reaction involves the inorganic reagent in solid phase, but still we have to make some addition of few drops of water into the system. Why is that so? Because when we add a little amount of water, then water forms a third phase, and this third phase is called the omega phase, right? So this third phase or the omega phase is formed as a surface of your solid reagent, right? What happens that in this thin film of water, that's the omega phase, the solid reagent gets dissolved, and from here the solid reagent will get shifted from the omega phase to the organic phase, right? So it's not only shifting of your inorganic reagent directly from the solid phase to inorganic organic phase, but actually by addition of small amount of water, we just add few drops of water. So what happens that a thin film of water is formed at the surface of your solid reagent. So this thin film of water is called the omega phase, and from here the omega phase, the phase transfer catalyst will carry the inorganic reagent from the omega phase to the organic phase, right? So we are not saying it as aqueous phase because it's just a thin film, it's not properly the aqueous phase, but we are saying it as omega phase. So that's all about the phase transfer catalyst and the type of phase transfer catalyst processes. So we have seen about the liquid-liquid phase transfer catalytic processes, and we have also seen about solid-liquid phase transfer catalyst properties. Right, each of them have their own mechanism and have their own applications. So I hope that you have understood this lecture well. Thank you for your attention.